The weak force is short range. And we can understand that if the particles that convey that force are very massive. And one of the great discoveries, in the 25 years ago now, was at CERN, not with the Large Hadron Collider, but with the machine that preceded it, was the discovery that these particles actually exist. W and Z bosons that convey the weak force, they're 100 times the mass of the proton. So that's why the force is weak, and that's why it's short range. But how can these two different forces be different manifestations of the same thing and be described by the same mathematics? The answer is, if at a fundamental level, all the forces look the same and the particles that convey all those forces are massless. That's the only way you can produce a mathematically consistent theory that unifies the weak and electromagnetic forces. And then they look identical. And you say, well, that's fine, but that's not the world we live in. And that's the key point. That isn't the world we live in. Because if we make a presumption, and that presumption is so presumptuous and remarkable, if we presume that there is this background field, invisible field permeating the entire universe that we can't see, and if the particles that convey the weak force, as they move through space, interact with that field and experience a resistance, like swimming in molasses, they will act heavy. And if the photon doesn't interact with that field, it will remain massless. So the fact that these forces appear to be different on our scale is an accident of our existence. An accident due to the existence of a background field in empty space. Our existence derives from the property of nothingness in that sense, as we'll talk about in many other ways. Now that is amazing and too good to be true. It seemed to me too good to be true. But positing invisible forces is the work of religion. In science, if those invisible fields are there, we have to measure it. And quantum mechanics tells us that if we slap the vacuum really hard with a lot of energy at a local point, if we can get enough energy and put it together at a small enough point, out of that field, we will pop particles. That is a property of the quantum universe, quantum field theory. So if the Higgs field is there, sounds nice, we can create Higgs particles out of that field by hitting it hard enough. And for the last 50 years, that's what we've been trying to do. And 25 years ago, almost 20 years ago, in this country, we would have done it. But Congress, in their wisdom, and at the time we thought they were stupid, but by comparison, it's just amazing. They killed the superconducting super collider in Texas, in spite of the fact that it was already built the biggest tunnel in the world, 60 miles around, and it was already built. But they decided the nation couldn't afford the $5 billion project, which is, of course, the air conditioning costs in Iraq war for one day. But, yeah, it's a sad thing. And finally, but what we knew was the only machine that could potentially do it, and this is why we're so excited, the only machine that could potentially do it was the Large Hadron Collider, and we've been waiting. And indeed, the Large Hadron Collider has detected a particle that seems to have the properties of the Higgs field, of the Higgs particle that should be associated with the Higgs field. And if that's the case, I was betting it was wrong. Because we're always wrong. We don't celebrate that enough. But for the most part, we're always wrong because nature surprises us. And I was betting on nature. I was betting that nature would come up with a better argument than this weird background field that just seems so slimy and so simple. But it's true. And that is even more remarkable in a sense. So the discovery of the Higgs field validates this incredible, beautiful picture of the Standard Model by saying that these two forces in nature are really manifestations of the same thing, and the particles that convey one force get mass accidentally. Not on a fundamental level, just because they happen to live in the universe we live in. Or most of us live in. Except the Republican candidates, as they often say. But then we, of course, if it's good, physics is like Hollywood, if it's good, you repeat it. And so, if it worked for the W and Z particles, maybe the other particles in nature, many of them, would get their masses from exactly the same thing. And the particles that are heavier would interact more strongly with the Higgs field. The particles that are lighter would interact less strongly. And the particles like the photon that don't interact at all remain massless. And that's the picture we now have, and it is amazing. And that leads to the final aspect of the Higgs field, which allows me to actually make this that way to whatever time I have remaining in the next couple of hours, to talk about nothingness. Because just think about it. It means that our existence, the existence of stars and galaxies and the universe that we live in, that we can see and celebrate, derives from these properties of an accident. An accident that has to do with the seeming properties of empty space. What could be more amazing? And that's really, for me, the real value of building machines like this. Not that they do anything useful, because they don't. I mean, they do. We'll revolutionize computer technology and all the rest. But that's not the reason. You don't justify something by the side benefits. You don't justify the space program by TAM. Although TAM is probably the only useful thing that came out of the human space program. And Neil Tyson isn't here to pretend that it was different. And anyway, I digress. But that's the value of our intellects. That's the value of our culture, of great art, of great music, of great literature, is to change our perspective of our place in the universe. And it's the value of great science. That's what makes science worth doing. It's not the technology alone, although it's responsible for our current civilization. It's the ideas. And what weirder idea than that our existence derive from this invisible field that actually is out there. And of course it changes our ideas of nothingness, which now allows me, there's the Higgs particle. Okay. So, I want to now spend a little time talking about nothingness, which of course is the subject of my most recent book, and in particular addressing the question, which is a nagging question, which has been nagging people since as long as people have been asking questions, which is, why is there something rather than nothing? Which really means, well, how do we get everything we see? And I actually just made that connection in a way that I should stress. I am using the word why colloquially here. We always ask the word why, but why has no meaning. Why is meaningless. The why questions are always meaningless. And if you have kids, you know that. Why? The only answer ultimately is because. Shut up. Shut up part. But people don't realize that, okay? Because why presumes purpose. Why implies there's some purpose. So if you ask, why are there 9 planets? And there are 9 planets. Again, Neil isn't here to pretend. Pluto is a planet, will always be a planet. My daughter did her 4th grade project on Pluto, and she's not going back and repeating 4th grade. And so when we say why, what we mean is how. Whenever we ask why, we really mean how. We really mean how are there 9 planets. Now, at some point, when you presume purpose, and Kepler may have asked, why are there 5 planets? And he might have meant some real why, that there was some purpose, that the Platonic solids somehow were related in some divine way to the creation of the universe, and there was a purpose to 5 planets. But we now know better. We now know when we ask why are there 9 planets, we mean how, and what we mean by how did there get to be 9 planets in our solar system is a characteristic of all solar systems, because now we know that almost every star has a solar system. That there are 2,000 planets already that we've discovered, and some solar systems are different. So why did ours get 9? Why does ours have rocky planets where they are? Why? And what we mean by why is how. So we can understand ourselves. So what I want to talk about is how is there something rather than nothing? And as I just illustrated with the Higgs field, the amazing thing that we should celebrate is these words do not mean what they used to mean. There's nothing wrong with that. It's bothered some people I talk to, they're called philosophers. And some of them, not all of them, are upset by the fact that we redefine these words, but that's what science does. It changes the meaning of things because we learn something. We learn something from nature. And when nature teaches us things, it changes the meaning of stuff that we discussed earlier when we were ignorant. So we may have some, Aristotle or Aquinas may have discussed what nothing was, but they didn't know any better. And so I want to talk about this, and what is truly amazing is that not only have these ideas changed, but to me, the greatest thing to celebrate is that we have a plausible understanding of how the universe and everything we see in it came from nothing without any supernatural shenanigans. And that is worth celebrating. Yes, you can spot that. And we don't know all the answers. You know, I sometimes read reviews. I try not to, but we don't know exactly how it works. We have a plausible understanding, and I want to show you. And perhaps, since I don't know how much time I'll get, because I just spent more time in the Higgs than I planned, was the amazing thing about the universe we see is we can ask what the characteristics of a universe that would come from nothing are. And they are precisely the characteristics of the universe we see. That is amazing. And you know, my friend Richard Dawkins wrote a rather over-the-top afterword of the book where he was nice enough to compare it to Origin of the Species, which is good for sales and all. But you know, it is over the top because Origin of the Species is one of the greatest scientific books ever written, and mine is up there, but not. But anyway, but the idea is not that crazy in the sense, in a general sense. Before Darwin, life was a miracle. Every species, every form of life with special creation was created with a purpose in mind to fulfill it. What Darwin showed was that it was plausible to understand the incredible diversity of life on Earth from a simple origin of a single organism by natural selection and mutation. He didn't know about DNA or the details of genetics, but the mechanism was plausible, and then not only that, he looked at those life forms and said, if I ask the question, could they arise by natural selection, the characteristics of everything we see are precisely those that we would expect for life to have arisen by natural selection. And that's where we're at, we're with the universe, and that is truly amazing that we've come that far. And that's what I want to celebrate with you in the next few minutes. And I'll try and do it. And again, I know I've talked a lot in different contexts, so I'm going to try and emphasize, I'm going to try and review some of the stuff that some of you will have heard on YouTube or wherever the hell you've seen me. But I want to emphasize some things that haven't been discussed on those things for you all, and be a little more detailed. So, when you ask the question, why is there something rather than nothing, you could begin this way, and then you can write a book about it. But that doesn't explain anything. What we want to do is get our understanding from the universe. And so this is a picture of a globular cluster in the night sky. It's beautiful. And what we have learned, indeed, is this picture, by the way, you know, is representative of what humans saw for most of their evolutionary history. Look out at the night sky, beautiful stars, fixed in the cosmos. And what I should emphasize is that our picture of the universe has changed so tremendously. 100 years ago, the picture of those stars, and the scientific picture 100 years ago, was that we live in a static, eternal universe with a single galaxy surrounded by an eternity of empty space, of darkness. Might as well have been the darkness of the Bible, the void. We now understand, as Sean mentioned, that there are almost 400 billion galaxies, each containing 100 billion stars, and we knew of one of them until a human lifetime. And not only that, we know the universe is static. We know it's expanding, thanks to Edwin Hubble, 1929. And I'm not going to, as I say, if I were giving the pedagogical version of this, which some of you heard, I'd go into that a little bit. But Hubble discovered and convinced the world that the universe was expanding by looking out and seeing that the galaxies around us are moving away from us. And then the natural question became, what's going to happen? How's it going to end? Is the expansion going to stop and recollapse? Is it going to go on forever? Is it going to slow down and never quite stop? And that's the reason, by the way, I got into cosmology. I'm a particle physicist by training, but I wanted to be the first person in the history of the world to know how the universe would end. It seemed like a good idea. Because it was particle physics, as you'll see. So anyway, I put this nice pretty picture in because Einstein told us that you can understand the expanding universe, but in particular, Einstein told us in 1919 that space is actually curved. Space is curved in the presence of matter and energy. And our universe can exist in one of three geometries, and these are curved three-dimensional universes, but I can't draw them. So I can draw curved two-dimensional universes, so that's what's up here. And our universe can be so-called open, closed, or flat. An open universe would expand forever. A closed universe would expand and stop and recollapse, and a flat universe was just the boundary between the two, which would slow down and never quite stop. And the business of cosmology for the next 80 years was, which universe do we live in? And that's what I wanted to answer. And as I say, when we talk about the kind of universes we live in, people get the idea that a flat universe is like a plane. It's not. A flat universe is just the universe you always thought you lived in. It's a normal three-dimensional universe where perpendicular axes remain perpendicular. And a closed universe is one where that's, and open where that's not the case. And you can think about it heuristically. In a closed universe, if you look far enough in that direction, you'll see the back of your head. The universe will curve around and stuff. Sounds nice. It's great for cocktail parties or picking up girls at bars or whatever you want to do. But I want to show you now the big question: which universe do we live in? Has now been answered. It's amazing. And it's been answered quite simply because Einstein said if mass curves space, you just have to know how much matter there is. All you have to do is weigh the universe. It's really simple. As Sean said, the hard stuff is, this is the easy stuff. Let's weigh the universe. And we can do it with a picture. And here's the picture. And it's a wonderful story that I wish I had time to tell about Einstein, but I'm not going to. And this picture. But this is a picture that is remarkable. Well, it's a Hubble Space Telescope picture, and they're all remarkable. Every dot in that image is a galaxy, not a star. And we can talk about that in a second. But this is an image that proves that space is curved. Because Einstein actually predicted, although he didn't understand how useful it would be, in fact he thought it would be useless, that if matter curves space, then if I have a big enough mass distribution, it can act like a lens. I can have a light source behind a big mass distribution. The light can go around and it'll bend and curve and come back and be focused, like my glass is focusing, and magnify things. Or if I had a cut glass goblet, it could produce many images of the object. This is exactly that phenomenon. It's called gravitational lensing. It's space acting like a lens. This image, all the galaxies in there are part of a large cluster of galaxies. Galaxies live in clusters. Our galaxies are clusters. This cluster is 5 billion light years away. So that light from these stars left those galaxies before our Earth and Sun even existed. And most of the stars in that picture don't exist anymore. And the civilizations that may have existed around those stars don't exist anymore. Every time I look at a picture like this, it's unbelievably inspiring. Because it just, how can you not think about the universe when you see things like that? But you don't have to be a rocket scientist to see that in that picture are blue things. I get tired of not being able to point here. Blue things. Those don't look like the yellow things. And those are multiple images of a single galaxy located 5 billion light years behind that cluster, 10 billion light years away. A galaxy we wouldn't be able to see if it wasn't magnified by space. And because gravity also acts like, as I say, like a cut glass goblet, it produces many images. All of these images, the blue images, are images of precisely one galaxy that's multiply imaged, distorted. And it's beautiful. It tells us that space is curved. But now we understand general relativity, so we can use it. And we can say how much mass must exist in that galaxy, or those clusters of galaxies, in order to produce the image. And it's a very mathematically complex problem. It's called inversion, but we can do it. And we do it. I'm going down again. When we do it, this is the picture. This is where the mass is. And you can see that each of the spikes is where the galaxies are. This is where the mass would have to be to produce the image that we see. And what you see is, well, there's spikes where the galaxies are, but most of the mass is where the galaxies aren't. There's a mountain of mass where the galaxies aren't, where there's nothing but darkness. In fact, there's 40 times as much mass in that picture as meets the eye. 40 times as much mass as what shines. And physicists, because we're so creative, call this dark matter. And we now understand that not just this cluster, but in fact each of the individual galaxies has huge amounts of dark matter around it. Over 90% of the mass of our galaxy is invisible. You can away, and it's invisible. And we understand that there's so much of it that it's not made of normal particles. It's not made of protons and neutrons like the particles in your body. It's made of some new type of elementary particle. And that's what makes it interesting, because it's not just out there. It's in this room, going right through your body, says you not off now while I'm talking. But we could go deep underground in Las Vegas, which as far as I'm concerned would be just as well as being on the surface. But in any case, and we can look for that, and we build detectors underground. Here's a nice detector. We cool it down to near absolute zero, and it's, I think I won't spend time talking about it, although it's actually one of the ones I proposed about 25 years ago. We can look for those particles and then discover the makeup of most of the matter in the universe, a new type of elementary particle. And what makes it even more exciting, and what makes the whole story neat, is that we don't have to wait. These particles were created at the beginning of time, we think, these dark matter particles. But if our theories are right, we can also create them in a place that reproduces the conditions of the early universe. Where is that? The Large Hadron Collider. And so there's a race right now between the Large Hadron Collider, which is trying to create these kind of particles, and the direct detectors, and we'll see who wins. We hope they both do. Or neither will. We'll find out that our ideas are wrong, perhaps, and that the dark matter is made of something else. But if we discover it, it will tell us what the most of the universe is, and it isn't us. Because that's the two lessons I want to really convey. The first one I've already sort of conveyed is you are far more insignificant than you ever imagined. In fact, you'll see you'll get more insignificant. And I'm talking about you, not me. But you'll see in a few minutes it'll be even more insignificant. Look, we are just a bit of cosmic pollution in a universe of dark matter and something else. In any case, we don't have to know what it is. We've already been able to estimate how much of it there is, and I want to show you the answer. And so, drum roll. Let's see. Oop. No, I thought I had it there. Maybe it's not. There we go. I couldn't see it. Can you see it at the bottom of that screen? I can hear that some people are fainting because they're so amazed. So, you know, in physics, whenever something is important, we give it a Greek letter because we like to sound scholarly. And but what this is the ratio of the total amount of matter in the universe divided by the amount you need to make an exactly flat universe. If it's less than 1, the universe is open. If it's bigger than 1, the universe is closed. If it's equal to 1, the universe is flat. And after 85 years of trying, we now have the answer unambiguously. There's only 30% of the amount of matter needed to make the universe flat. The universe is open. Case closed. But it's not closed because we theorists knew the answer. We always know the answer. We're very rarely right, but we always know the answer. And we knew the universe was flat. And that's because a flat universe is the only mathematically beautiful. And these damn observers were getting it wrong, as they always do. So the question is, well, this is a very indirect way to measure the geometry of the universe by adding up the mass, plugging into Einstein's equations, figuring out the geometry. Wouldn't it be better to measure the geometry directly? And the point of, go back to that old picture, is you can see I've drawn triangles on each of those universes. And a triangle looks like a normal triangle in a two-dimensional flat universe, but in a closed two-dimensional flat universe, if I add up the angles of a triangle, it's different. It's not 180 degrees. It's more than 180 degrees in a closed universe. And it's less than 180 degrees in an open universe. It turns out that that mathematical fact is true for curved three-dimensional universes. If we could just measure a big enough triangle in our universe, we could measure the geometry of the universe directly. And that's what we've done in the last, little over the last decade. It's amazing. We've done it by taking a surface as far away as we can look at and making the biggest triangle we can draw. And the surface is the surface that comes from the cosmic microwave background radiation, the afterglow of the Big Bang, discovered by accident in New Jersey, of all places, by two people who didn't know what the hell they were doing. But they won the Nobel Prize anyway, because you really don't have to know what you're doing to win the Nobel Prize. No, you don't. You just have to discover something. And I don't mean that in a bad way, although I will in a minute. In any case, when we look at the cosmic microwave background, comes to us from a surface that occurred when the universe was 300,000 years old. And that radiation was streaming at us and cooling down. And we were able to take a picture of that surface. Here's an experiment in the South Pole, the boomerang experiment, that was a balloon and a microwave radiometer that went around the world, which is easy to do in the South Pole, or in Antarctica, in the South Pole, you just do this. But what this does is give us a picture of the baby universe when it was 300,000 years old, which is amazing. But the nice thing about that picture is how big are those blobs? We understand those blobs represent matter that was collapsing when the universe was 100,000 years old. But gravity travels at the speed of light. And that means that no information can travel faster than light. Means if I have a blob that's smaller than 100,000 light years, it'll collapse. 100,000 light years, it'll start to collapse. But if it's bigger than 100,000 light years across, it won't know it's a blob. It'll look like Wile E. Coyote when he goes off the cliff in the TV shows. You hang around for a while before you fall. And so the largest blobs that could collapse are 100,000 light years across, but that gives us a ruler. It's a ruler that's 100,000 light years across, a known distance away from us, connecting the points to us, makes a triangle. And if we live in a flat universe, we can say that ruler will be 1 degree across on our eye. If we live in an open universe, the ruler will look smaller, maybe half a degree. If we live in a closed universe, it'll look bigger, maybe 2 degrees. So all we have to do is ask, how big are those blobs? And we've measured the geometry of the universe directly. And so here's a different false color image from the boomerang experiment. And the real universe is up above. And here are universes we created on a computer. And there's a closed universe, a flat universe, an open universe. And in a closed universe, this is how big 100,000 light year across blobs should look for us now. But that's bigger than these lumps. In an open universe, this is how big the blobs should be, about that size, but those are smaller than those blobs. But just like Goldilocks, in a flat universe, it's just right. We live in a flat universe. In fact, I think, I'm going to blind you with science, I think this is actually a prediction of the sort of number of blobs as a function of the size of angles. This is the prediction for a flat universe, and that's the data. Most of the blobs are about 1 degree. We now know with 1% accuracy that the universe is flat. An amazing achievement of humanity stuck here in the middle of nowhere, especially in Las Vegas. Now, that's amazing. But you will remember, if any of you have been conscious during the last few minutes, that a few minutes ago I pointed out to you that we knew the universe was open. We only had 30% of the amount of stuff. 70% is missing. Well, where could that be? Well, if it's not where the galaxies are, it has to be where the galaxies aren't. But what is where the galaxies aren't? Nothing. And that's the point. If Einstein tells us if we put energy in empty space, and what I mean by that is if you take space and get rid of all the particles and all the radiation and everything, there's nothing there. If that space weighs something, which is crazy, then it's gravitationally repulsive, not attractive. All of you learned that gravity sucks in high school. It always pulls, and there are pushes. But if you put that energy in space, it pushes. And in 1998, 2 teams of astronomers who didn't know what the hell they were doing were trying to measure the speed at which the universe was slowing down, because any sensible universe should be slowing down due to gravity. And what they discovered, so what they discovered was something quite different. In fact, if the energy of the universe resides in empty space, it's gravitationally repulsive, and the universe won't be slowing down. And much to their surprise, and they published it in 1998 or so in the cover Science. Well, yeah. Let me actually show the picture first. Let me skip, because I'm going to skip some stuff, which is wonderful, but I don't have time. This is the picture that they gave of the rate at which the universe is slowing down. It's hard to understand, but let me draw a straight line through it and make the straight line horizontal. And if the universe were slowing down, all of these objects, exploding stars that are observed billions of light years away, would follow this dashed curve down here. That's what they expected to see. And what they saw instead is that objects fell above the straight line. Now, there's only 2 ways to explain that. 1, the data is wrong, which it usually is. Or 2, the universe is accelerating. The expansion of the universe is speeding up. And that is remarkable. Now, if it's true, and the expansion of the universe is speeding up, it's due to the energy of empty space. How much energy would you have to add to empty space to make it speed up? Well, let's fit the data with that straight line. And what do you need? You need exactly what we're missing. If you put 70% of the energy in the universe in empty space, everything works out. Except, it's crazy. The dominant energy of the universe resides in empty space. We don't have the slightest idea why it's there, which is so wonderful. And as I often say, if anyone comes here and tells you they understand it, they're lying, especially if they're a string theorist. Its existence is probably tied to the physics that explained to us the beginning of the universe, and as I might get to in the end of this talk, which will hopefully take place in a time less than the actual future of our universe, it will determine our future. But we understand now that we live in a cockamamie universe, 30% of which is dark matter, 70% of which is this energy empty space. We call it dark energy because we're so clever. And 1% is us. We are a 1% bit of cosmic pollution. That's why you're even more insignificant now than you were 15 minutes ago. We are nothing. The universe, so much of our universe that was created for us. We are just bystanders in a universe full of dark matter and dark energy, and that's where the real action is. Okay. Now, why do we think the universe is flat? Now, here's some stuff I don't think I've talked about in any media, but maybe. The reason I got into it is quite simple. We think we can understand how the universe is going to end because we learned high school physics. And you all learned high school physics and loved it. If you have a coin, I don't have one. I threw it up, it comes back down. If I throw it up faster, it takes longer to come back down. If I throw it up really fast, it doesn't come down at all. And we teach high school students in other countries how to and I'm going to take you back to a wonderful time in your life. I'm going to write down an equation. We say that the coin has energy, and there are two pieces of the energy. There's a positive piece, the kinetic energy, and a negative piece, the gravitational energy, and those two pieces add up. And if the total energy of the coin is positive, it just becomes accounting. If the total energy of the coin is positive, it'll escape from the Earth. If it's negative, it'll come back down. So we just have to see if we give it enough positive energy, and that, you notice the positive piece is the mass there, I think. There's the mass, there's the velocity. And the negative piece is the gravitational attraction, which is the mass. So you just keep speeding it up, and eventually it escapes. The positive piece wins out over the negative piece. 11 kilometers per second with the surface of the Earth will take something and make it escape. Well, the same is true for the universe, because the universe is expanding. Here's the view of these are galaxies, not sperm, as I like to point out. And if we're at the center and we're looking out, galaxies are moving away from us. And if the universe is the same everywhere, then what happens to a single galaxy should happen to every galaxy. So we just have to ask, what's the total energy of that galaxy? There, any one of them, but let's take that one. The positive piece comes from its velocity, but the velocity comes from the expansion rate of the universe, which we measured. The negative piece comes from all the mass that's pulling it in, the dark matter and all the rest of the stuff, which we've measured. And then we just compare the two. If B is bigger than A, the negative piece is bigger than the positive piece, the universe is going to collapse, we thought. If B over A is less than 1, the universe is going to expand forever. And it turns out, amazingly, that B over A is this quantity omega, the curvature of the universe. And we've discovered what omega is. Omega is 1. We live in a flat universe. So B is exactly equal to A. What does that mean? The negative piece is exactly equal to the positive piece. What does that mean? The total gravitational energy of every object in the universe is 0. Now, if you were going to create a universe from nothing, what would you make that energy? Okay. Now, that's what I just put up there. So I want to talk about the different kinds of nothing in the last bit of this talk, because nothing seems to be a very confusing topic. So when I say a universe can come from nothing, the first kind of nothing is just empty space. Empty space itself. And the amazing thing is, the simplest answer to the question, why is there something rather than nothing, is nothing is unstable. Because as we try and understand the energy of empty space, which we measure now, we know that empty space is not such a simple thing. We've just learned from the LIC that empty space contains Higgs field, for example. But even more interesting, perhaps, empty space, we know, at a quantum mechanical level, is a boiling, bubbling brew of virtual particles. This picture I showed earlier, but I want to show it again anyway, and explain it this time. This is the space inside of a proton. This is a mathematical calculation of exactly what it looks like inside a proton. And the interesting thing is, these are virtual fields popping in and out of existence in a time scale so short you can't measure them. That sounds like philosophy or religion. But in fact, we can't measure them directly, but we can measure them indirectly. And in fact, we can measure their effects indirectly. In fact, these virtual fields are responsible for all of the mass of your body almost. Not the Higgs field, these ones. So we know they're there. And then we try and calculate what they should contribute to empty space, and we come up with a figure I showed earlier, but I zip-bobbed, we come up with the worst prediction in all of physics. We don't understand it. This process should give empty space 120 orders of magnitude more energy than we measure. So there's a small error there. So we don't understand it, but we think, well, okay, we know that these processes are happening. And if they're happening, it turns out if you add gravity to the mix, you create virtual particles. The reason they have to disappear in a time scale so short you can't measure them is the Heisenberg uncertainty principle of quantum mechanics, which says, like the White House and corporate America, if you can't measure it, anything goes. And on small scales, anything can happen, and these virtual particles can pop in and out of existence, violating energy conservation, but they go away before you can measure them. But if the two particles that are produced, a particle-antiparticle pair, have zero total energy, they can survive with impunity. And when you add gravity into the mix, you have negative energy as well as positive energy. So if you create particles that have enough gravitational attraction that can balance the gravitational pull, you can create particles that survive. And in fact, therefore, quantum mechanics tells us if you have empty space and you wait long enough, you will always have something. So the big question would be, the interesting question would be, not why is there something rather than nothing. If there was nothing, that would be interesting and unexpected, but you wouldn't be there to ask the question. So empty space, the kind of nothingness of the Bible, a vast, dark, eternal void, is simple. It'll always create something. But some people say, well, you know what? That's not empty space. That's not nothing. It's empty space, but it's not nothing because where's the space coming from? The interesting thing is that that's what I just said here. Maybe I should emphasize that what I've shown you is the first real miracle that I've talked about here, or what would otherwise be considered a miracle if it weren't science. We can create everything we see. And if I ask myself, what interested Aquinas or Aristotle or any of the people who asked the question, why is there something rather than nothing? It was the question, how can you get all this stuff if you started out with no stuff? It should violate something. And once energy is created, people say it should violate energy conservation, but it doesn't. You understand how you can get a universe full of galaxies without any supernatural shenanigans. That alone is amazing. Now, the second kind of nothing, turns out if you apply quantum mechanics not to just particles in space, but to space itself, then space itself becomes a fluctuating thing, and you can create universes, spaces from nothing. You have no space, no time, and suddenly, burp, space and time, a closed universe, or a universe. That happens all the time. It's happening right now. But most of those universes collapse in a microscopic time scale. What's the only kind of universe that can survive long enough for us to be here to ask the question? A universe with zero total energy. Now, it sounds nice because I just told you our flat universe has zero total energy, but I lied. I said it had zero total gravitational energy. It turns out when you do this a little more carefully, the only kind of universe we know of that we can prove mathematically has zero total energy is a closed universe. But you say we don't live in closed. But most closed universes, as I pointed out to you, will collapse. And they'll collapse at a time scale that's microscopic. How could you make a closed universe survive for at least 13.72 billion years, which is how old the universe is, everywhere except for Arkansas, Ohio, and a few other places? Our universe appears to be flat. Well, the point is, most closed universes will collapse. But if we give empty space energy at some early time, empty space this gravitational repulsive, it'll puff up that closed universe to a huge scale. And just like blowing up a balloon, if you puff up a balloon and look at it, if you're living on the balloon or the surface of the Earth, it looks flat. So the only closed universe that can survive for a long time is one that got puffed up by some process with the empty space having energy in early times. And then it would look flat today. And that's just what we predict. We predict at early times that there was exactly an energy, a very large energy of empty space. It caused the universe to increase incredibly in a fraction of a second in size, 90 orders of magnitude in volume in 10 to the minus 35 seconds. It's amazing. And it sounds like it's impossible and too good to be true. But if it happened, then quantum mechanics, it turns out, while that's happening, will produce fluctuations in matter and radiation, and they look exactly like the fluctuations in matter and radiation that we see in the cosmic microwave background. So we think that theory of inflation is correct. And I want to point out that we now think it's even more correct because of beer. We'll see more correct later tonight. But many of you, if you're like me, if you're ever at a party, you forget to put the beer in the fridge. And what you do is you put it in the freezer. But you forget. And then you come out and you take the beer out of the freezer, and it's got a beer bottle, you open up, crash! Because it was liquid, and then the minute I open the bottle, boom, it freezes, breaks the bottle. Because the beer was super cold. And when you let it out, boom, it went to ice. And it released a lot of energy when it did. We think that's what happened in the early universe, is energy that got stuck in empty space. As the universe cooled, went through a phase transition, was released, producing all the energy we see for all the galaxies and stars and everything else. And what's neat about that is that mechanism requires that there be a field permeating empty space at early times, and now we know that idea is not so crazy. It's not the Higgs field, but it's a field just like the Higgs field, and that whole intellectual house of cards could have fallen apart if our ideas about the Higgs field were wrong, but they're not. Yeah, okay. So, the bottom line is, inflation will force the universe to appear flatter, and it will force the universe to look just like the universe we live in. So you can ask, what universe could come from nothing? A universe, a closed universe created with zero total energy, but the only one that could survive would puff up by inflation, look flat, and what do we see? We see that we live in a universe that looks flat, that appears to have been puffed up by inflation. The only kind of universe that could have been created from nothing. Okay, that should be good enough. People say you don't have space, you don't have particles, you don't have space, but you got the laws of physics. Who made the laws of physics? And the point is, even the laws of physics themselves may be accidental. Now, I see I have 5 minutes left here, but I did kill 4.5 trying to get that stuff done, so I don't know. I should ask, can I go my 5? Can I use up that time? Or no? The time I lost? Well, we will. Doesn't matter. But, you know, Penn and Teller on next, so we don't want to make it too long, because they're much more interesting. Let me tell you something that's driven physicists crazy. We have returned to the center of the universe, which is upsetting. Because this is the brief history of time. This is a history of the density of matter as the universe expands, goes down as the universe expands. The energy density of empty space remains constant, and we live here right now, where the energy density of empty space is 3 times that of matter. But you'll notice, and this is what's bothered people, is we live in the only time in the history of the universe when those two numbers are the same, within a factor of 3. Why? Why should this happen 13.7 billion years after the Big Bang? It's a random time, nothing special about it. Copernicus told us it's not supposed to be that way. But physicists have come up with a potential answer. And it's not a very good one. Well, it's a good one, but it's not a very nice one. But as I want to point out, the universe doesn't give a damn whether we like it or not. If it happened, it happened. And the answer is that there are galaxies. Now, why is that the case? Well, let's say the energy of empty space were 50 times what it is now. There. These two curves would cross not today, but at a different time. What time? That happens to be the time when galaxies first formed. But the energy of empty space is gravitationally repulsive. If it dominated the expansion before galaxies formed, galaxies would have never formed. The matter would have been pushed apart before it could collapse. And if galaxies didn't form, well, that should tell us something. And so people have proposed, and I call it anthropic mania, maybe there are many different universes. And maybe the energy of empty space can vary in each one, then only those in which it's not much greater than what we measure today will galaxies form. And only then will planets form, stars form, planets form, and then astronomers. The universe is the way it is because astronomers are here to measure. Sounds ridiculous. Sounds religious almost, but it's not. It's just cosmic natural selection. If there are many universes, we would be manifestly surprised to find ourselves living in a universe in which we couldn't live. It's just like bees and flowers. They're not created and designed to be able to see the colors of flowers. If they couldn't, they wouldn't be able to reproduce. They wouldn't be able to survive. And so it may be that this fundamental property of nature is an accident. Now, particle physicists have picked up on that because we're way ahead of cosmologists. Because there's one fundamental number we don't understand in cosmology, which is the energy of empty space. But in particle physics, there's many more quantities we haven't understood for much longer. Way ahead. We don't understand why gravity is the weakest force in nature, why the proton's 2,000 times heavier than the electron, why there are 3 generations of elementary particles. We don't understand any of that stuff, and we used to like to think we could try and explain it. But some people have said, hey, maybe it's all an accident. Maybe all those constants of nature are just accidents, random variables in many different universes, and then they have to be what they have to be in order for us to be there. And if that's the case, we don't need a theory of everything. We just need a theory of anything. And I cannot resist but point out that some people think we have such a theory. It's called string theory, and I can't resist with it. This is my favorite comic strip. And this is a brief history of string theory. One guy said, I just had an awesome idea. Suppose all matter and energy is made of tiny vibrating strings. The other guy says, okay, what would that imply? First guy says, I don't know. So that's the history of string theory over the last 40 years. But what it may suggest, it turns out string theory says there are maybe 11 dimensions, they compactify, maybe 4 large dimensions, but every different way you compactify the extra 7 dimensions, you get a different universe in 4 dimensions. So maybe there are an infinite number of universes. Maybe they all have different laws of physics, but if that's the case, the laws of physics come into existence at the same time as the universe does. It's random. And in that case, you don't have any particles, you don't have any space, and you don't have any laws. And it seems to me that's a pretty good definition of nothing. The last kind of nothing, which I will talk about in the last 3 minutes, is in deference to Christopher Hitchens, who was a good friend of mine, and I know we've thought of here already, and it's a loss for all of us. I used to be, as I pointed out in his memorial service where I was asked to speak, his personal physicist. And that was a great honor. And I told Christopher, who was writing the foreword for this new book before he died, and he never got to finish it, what was happening, and the fact that the universe would expand, and in fact, I'm going to skip through this beautiful picture I had of a miserable future, but I'm going to skip it, because I was going to skip the joke I was going to give. But we can ask, what will the universe in the future look like? And the point is, the universe is expanding faster and faster. Eventually, all of the galaxies we now see will disappear. They'll be moving away from us faster than the speed of light. And what will the picture in the far future be for astronomers who evolve, and I can still use that word here, evolve around planets that live around stars in 2 trillion years, and there will be stars like our main sequence sun in 2 trillion years. They'll discover the laws of quantum mechanics, electricity, magnetism, gravity. They'll build telescopes to look out. What will they see? They'll see the universe we thought we lived in 100 years ago. All the other galaxies will have disappeared. They'll see one galaxy. The rest will be empty space, and all evidence of the expanding universe and the Big Bang will have gone away. And that's what I was going to spend a little time on, but I really don't want to go more than my allotted time. So I'll skip exactly one. But think about it. It means in the far future, the picture of falsifiable science will be false. And that should make you worry a little bit. We can talk about that, but I don't think we'll have time for questions, which is good. Now, but we'll have an empty space surrounding us, and eventually the stars in our galaxy will burn out, and we'll be left with a cold, dark, empty universe. And that's the second thing I wanted to tell you. First, you're insignificant. Secondly, the future is miserable. But Christopher put it a different way. He said, well, nothingness is heading towards us as fast as can be. So the real answer to the question, why is there something rather than nothing, is there won't be for long. And that, to me, is very important because it points out our cosmic conceit. We think we're the pinnacles of evolution, when in fact evolution is continuing on Earth. We think the universe was created for us, and it's always going to be this way. It ain't. We have to realize that the future is going to be different, and we just happen to be here at this instant. And that really is what should give meaning to connect to what Sean was talking about earlier. So to summarize, in exactly on time, in fact, science has demonstrated that a universe from nothing is not only plausible, but likely. What we mean by something and nothing has completely changed from the words that the classical philosophers and theologians came up with, but who the hell cares what they came up with? We should care about the nothing and something that describes the universe we live in. And we only learn about that by looking, not by thinking. The real question, the question why is there something rather than nothing, is not the interesting question. The interesting question is, how did the universe evolve, and how can we find out? And that's what we're trying to do with science. And we have come with our intellects in this remote corner in the middle of nowhere to understanding that. And although you are insignificant and the future is miserable, you should be happy. Because it's just so amazing that we know what we know. And that we can assess and we can judge and we can make meaning in our own lives, not from a universe that has no evidence of apparent meaning at all, or purpose, or even uniqueness. But the meaning we make is the meaning we have is the meaning we make. Thank you very much.